So you're like me and you're sitting in bioengineering class, listening to the professor talk about counting microstates and protein folding, but that makes you kind of hungry and you start wondering about eggs, in particular cooking eggs. Yum.
If you've ever taken any chemistry, you might know that when solids are heated up at a certain temperature, they become liquid.
Okay, so why then, when you cook an egg, does it go from a liquid-like goo to a solid?
To understand this, we need to talk about something called free energy. When scientists talk about free energy, they mean
All of the energy that a system contains that can be used to do mechanical work.
Here's the idea. Let's zoom in on some matter. Way in. We see that everything is made of little tiny particles called molecules that are all bouncing around randomly in every direction. Mass is energy when it's moving, so each of these little molecules has a little bit of energy.
we can add all of those little tiny amounts of energy up, and we'll have something called the thermal energy, because the faster these molecules move, the hotter the object is. We can use some of this thermal energy to do work, but not all of it, because it's too random. There's too much uncertainty about which direction each particle is moving.
In other words, some of this internal energy is usable, free, and some of it's unusable. In order to find the usable, free energy, we subtract away the unusable energy because of its randomness. Let's quantify this randomness. We could call it entropy and give it a symbol S for super unuseful.
The amount of unusable energy increases as temperature increases, because the hotter the object is, the more energy is invested in this random form. So we can multiply our randomness factor by temperature to find this unusable energy.
Finally, we'll see that our free energy is equal to our internal energy minus temperature times entropy. Now, it's a general principle of our universe that things tend to become more and more disordered, or random, simply because there are more ways to be arranged in a random fashion, high entropy, than there are ways to be arranged in a less random way, low entropy.
So it's more likely that you'll end up with a higher entropy. Higher entropy means lower free energy. Simple probability.
And that's the second law of thermodynamics.
Thanks, guys. So you mentioned that it seemed counterintuitive that eggs would solidify when we increase their temperature or cook them. Is an egg cooking an example of a system becoming more ordered? And is this a violation of the second law of thermodynamics, which states that entropy of an isolated system must always increase?
Probably not. So let's try to understand what's going on here. Let's zoom in on a raw egg white structure. Egg whites are composed of 90% water and 10% proteins. The proteins are assembled from chains of amino acids. The various amino acids in a protein chain interact with each other to create specific configurations. A few of the most common amino acid bonding interactions are displayed in these images. Since two parts are required to make this weak interaction possible, we can call one male and one female.
Since a protein often needs help folding into the right specific configuration, it is fortunate that chickens own tiny cellular machines called chaperone proteins to help out with this process. Once a protein is folded into the right configuration, chemical interactions within the protein help maintain its shape. However, these shape-maintaining male and female chemical interactions are quite weak when compared to the peptide bonds holding the individual amino acids of the protein together. In fact, they are weak enough that the additional jiggling and wiggling that we can induce by cooking an egg on the stovetop is enough to break these bonds apart, leading to the denaturation or unfolding of the proteins.
Normal or uncooked proteins are shown on the left. They are folded in such a way that the outer portion of the folded structure interacts with surrounding water molecules in a similar manner to how water interacts with water molecules. This type of interaction is called hydrophilic, or water-loving. The portions of the folded protein coiled inside don't interact with water in the same way. They react more closely to the way oil reacts with water. This type of interaction is called hydrophobic, or water-repelling. While the egg is being cooked, the protein structure created by the weak bonding is lost, and the protein unfolds into chains of amino acids, shown in the middle of the diagram, exposing the previously hidden hydrophobic amino acids to the environment. More importantly, the male and female parts of the individual proteins that were interacting with each other in folded position are now free to mingle with the male and female parts of all of the other unfolded proteins. Random configurations result because bonds are made to whichever opposite type happens to be within reach. Whether that opposite part is from the same protein or another protein nearby doesn't matter, as all of the proteins solidify into a massive molecular orgy.
Because they are no longer all hydrophilic, the unfolded proteins now interact with each other, becoming tangled and creating a much more interconnected structure that we perceive as being more solid. Additionally, a significant amount of the water evaporates, further increasing the solidity of the egg. So now we know what is going on, and we can see at least two places where entropy does increase. The first place is the evaporation of a significant percentage of the water molecules in the egg white, which, if you remember, is composed of 90% water. Remember that gaseous H2O has a higher entropy than liquid H2O. The second is in the random tangling of the unfolded proteins, which, in a similar fashion to the Sharpie disorder earlier in this video, experiences an increase in entropy because the molecules have a vastly larger array of possible configurations than when they are all coiled individually in the same configurations. So we have not found a violation of the second law of thermodynamics. The increase in entropy is merely somewhat hidden. So thank you for watching our video.